Okay. Next speaker is Jin-hui Fang. And take it away. Thank you.
Okay, thank you. Firstly, I would like to thank Professor Mel for organizing this meeting. It's my great honor to give a talk today. I am Jin-hui Fang from Nanjing Normal University, China. The title is Minimal Asymptotic Basis Related to G-adic Sequence. Firstly, let's recall the definition. Let H less than 2 be an integer. For a long-empty set A of integers and every integer n, let RAHN be the number of representations of n in this form, where A1, A2, and AH are all from the set A, and they are increasing. We often write RAHN as RAN for simplification. The set A of non-negative integers is defined as an asymptotic basis of order H if IHN is less than 1 for all large n. This means all large n can be expressed as the sum of H elements from A. Such A is further defined as minimum if no proper subset of A is an asymptotic basis of order H. In 1955, Stoll introduced the concept of minimal asymptotic basis. Hatter and Lassassen proved the existence of minimal asymptotic basis of order H for general H. In 1979, Edosh and Lassassen considered the relationship between RAN and the minimal asymptotic basis of order 2. They obtained this nice result. Let A be an asymptotic basis of order 2 such that RAN is larger than C log n, where C is a positive constant and n is large. Then A must contain a minimal asymptotic basis of order 2. In 1989, Edosh and Lassassen mentioned the following problem. Determine whether the set A must contain a minimal asymptotic basis of order 2 if RAN merely tends to infinity. Just now RAN is larger than C log n. Now, if RAN only tends to infinity, its n must contain a minimal asymptotic basis of order 2. In this paper, Edosh and Lassassen prove that for any integer t, there exists a set A of non-negative integers such that RAN is less than t for all large n, but A doesn't contain a minimal asymptotic basis of order 2. Inspired by the construction in this paper, in this result, recently I proved that there exists a minimal asymptotic basis A of order 2 such that RA2 multiplies 36 to the power k plus 1 is equal to 1 for all integers k less than 3. And all large n, if n is not equal to this, then RAN is less than c the square root of n. So for this n, IN is equal to 1. And for others, RAN is larger than c multiply the square root of n. Now let's see the second part. In 1974, by using binary representations, Lassassen explicitly obtained a minimal asymptotic basis of order 2. This is the first explicit construction for minimal asymptotic basis. Let X be the set of all finite non-empty subset of distinct even powers of 2. Y be the set of all finite non-empty sums of distinct order powers of 2. Let A be the union set of X and Y. Then such A is a minimal asymptotic basis of order 2. It's a very beautiful construction. Now, let's see a general construction. Let N0 be the set of all non-negative integers. Let W be a non-empty set of non-negative integers, and F star W be the set of all non-empty finite subset of W. Now let's see this definition. AW means this one, where the exponent is the finite subset of W. So just now, if W is the even part, then it's X. If the W is the odd part, then it's Y. Under this definition, an AW in 1989, Jia and Lassassen extended the above result to general integer H. Just now, Lassassen is the minimal asymptotic of order 2. Now, they further consider general integer H. Let H no less than 2, and let T be this integer. Then, partition N0 into H pairwise disjoint subsets W0 and WH-1, such that each set Wi contains infinite many intervals of T consecutive integers, where T is this value. Then the Euler set of AW0 and AWH-1 is a minimal asymptotic basis of order H. So this is an explicit construction for minimal asymptotic basis of order H. Okay, also in the same paper, Jia and Lassassen pose the following interesting problem. Let N0 be a partition such that omega is in Wi implies either omega minus 1 is in Wi or W plus 1 is in Wi. Is this set a minimal asymptotic basis of order H? So try to establish the relationship between the partition and such A is minimal asymptotic basis of order H. In 2011, Chen and Chen answered this problem. Let H no less than 2 and R be the least integers with R larger than log H over log 2. Let N0 be a partition such that each Wi is infinite and contains, contains R consecutive integers. Then such A is a minimal asymptotic basis of order H. So the partition must satisfy that each Wi is infinite and contain R in consecutive integers. So we may consider if R is smaller, what happens? 7 years later, Chen and Tao further obtain this result. Let H and T be integers with T is no less than 2 and no larger than log H over log 2. So we see that just now R is larger than this one. Here, T is no larger than this one. Then there exists a partition such that each Wi is a union of infinitely many intervals of at least T consecutive integers and this set A is not a minimal asymptotic basis of order H. So these two results are from the different direction. Okay, in 2022, Nasasen introduced the notation of G-adic sequence. We say that let di be integers no less than 2, and we define gi be the d1 multiplied d2 multiplied di. For example, if all di is equal to some integers j, where j is less than 2, then if d1, d2, di are all equal to 2j, then ji is j to the power I. It's a G-adic sequence. It's the usual G-adic representation. If di are all equal to 2, then it's a 2-adic representation. So under the general G-adic sequence, just now we define AW. Now we say under the G-adic sequence, we may define AJW. AJW means, well, Ji is in this Gi sequence. It's similar to the definition of AW. Okay, under the notation of G-adic sequence, Nasasen obtained a new class of minimal asymptotic bases. We recall that as the first Nasasen gives the first explicit construction of minimal asymptotic basis under 2-adic representation. Now, Nasasen obtained a new class of minimal asymptotic bases. We say that let H no less than 2, and let T be an integer such that T is no less than 1 plus log H over log 2. Let W, W0, WH minus 1 be a partition of N0, such that for every row I, there is an infinite set Mi of positive integers such that Wi contains at least T consecutive integers. Okay, let G be a G-adic sequence. Then the set AJW, this means the union set of this one, of AJ W0 and AJWH minus 1.
Hi, Rachel. This is Russell Hendel. Hope everything is okay. Guten Chodesh. Recall you invited me over when we were mutual guests at the Sentences. I said I was available for Eschanan, which is Shabbos lunch, July 25th.
Got it. But it's still showing.
Sorry for that. I couldn't hear clearly.
Sorry, Jin-hui. That was somebody who had their microphone on who shouldn't have.
Okay. Could you listening my voice clearly?
Yes.
Okay. Now I will continue.
Please. Yes. Okay,
thank you. Okay. Under this general G-adic sequence, Nasasen also shows that this set AJW is also a minimal asymptotic basis of order H. Okay, now we see that in the precondition, Wi must contain an infinite set Mi of positive integers. So also in the same paper, I improve this by only requiring that each W contains only one interval of R consecutive integers. No, we don't need to infinite. So let H, let T, these are the same as Nasasen's result. Let W be a partition and that each Wi is infinite and only require it contains T consecutive integers. Okay, under a G-adic sequence, this set is a minimal asymptotic basis of order H. Okay, this is my talk. Thank you for your attention.
Thank you very much. Are there questions for Jin-hui in the room or
from Zoomland. All right, let's thank Jin-hui Fang again. Excellent
Thank
talk.
you.
And our next talk starts in.
Thank you. So I will stop the share.